Thank you, April, for that nice introduction, and thank you, everyone, for being here today. As she said, my name is Leana, and I am a fourth-year PhD candidate at the University of Connecticut under the supervision of Dr. Marisa Crisosio and Dr. Kai Willa. I would also like to acknowledge our co-author, which is James Mahoney, before I start my presentation. So a little overview of my presentation today. I'm going to be talking about the background and motivation behind my research, the overarching goal of my research, and the method that I'm using to accomplish my goals, the development of a wavelength dispersive X-ray methodology to quantify sulfate and sulfide in concrete, the application of our method and some results that we have until this point, the future direction of my research, and then lastly, some conclusions that we have until today. So crumbling concrete is an issue happening today, not only in Connecticut, but worldwide. According to the Connecticut Department of Housing, more than 40,000 homes in eastern Connecticut face the possibility of a compromised foundation. This deterioration is the product of using sulfur-rich aggregate in concrete production. As we all know, concrete is a mixture of aggregates, cement, and water. Aggregates could have sulfur in the forms of sulfide. Cement has sulfur in the forms of sulfate. When the sulfides present in the aggregates combine with oxygen and water, they form sulfate, which is a secondary reaction that causes concrete deterioration and expansion. Although we know the mechanisms taking part into this reaction, we don't know how factors like exposure to calories, pH, moisture content, and age of the construction affect this reaction. So the overall arching goal of my research is to develop a risk assessment framework to evaluate the probability of deterioration as a function of time and the field conditions that I mentioned before, like the pH, the moisture content, and the age, in order to assist homeowner and stakeholders with decision making. So what's happening to these foundations? So this far, we have developed a wavelength dispersive X-ray fluorescence method that, when coupled with an elemental analyzer, can accurately quantify the amount of sulfur that is inside our concrete samples, and then is able to distinguish between sulfate and sulfide. And then lastly, we can find the pyrrhotite weight percentage by dividing the sulfide weight percentage into 0.39, and this number comes from our calculations and the mineralogy of the pyrrhotite that we have in Connecticut. So this table has all the data that has been analyzed by the Yukon team till today. The number of samples include all individual samples from all homes. Every home has typically between 3 and 7 samples, with the average home having 5 samples. Each sample consists approximately of 150 grams of homogenized concrete powder that is tested for total sulfur, and then WD-XRF analysis, in which then we can distinguish between sulfate and sulfide. And we do this in triplicates. For our statistical analysis, we have created 3 categories to divide our homes. So we have the NN homes, which means no damage, no pyrrhotite. When we say no damage, that means no cracks were seen when people went to the homes. And when we refer to no pyrrhotite, we say that the total sulfur concentration was lower than the detection limit of our method, which is 0.25 weight percentage of pyrrhotite in concrete. The other 2 categories are NP, which means no damage, and pyrrhotite was present, so we didn't see cracks, but we can see pyrrhotite through our method. And then the last category is DP, which means damage and pyrrhotite, so yes, we see crack, and yes, we can see pyrrhotite through our method. So the data that I will be showing you today come from 173 foundations, 700 plus analysis and samples, 700 plus samples, and then 4,000 plus analysis. So when we look at the total sulfur distribution of our homes, we can see that all no pyrrhotite, no damage houses have a total sulfur less than 0.3%. Then an increase in total sulfur means an increase in sulfide. However, the sulfate stays relatively the same. We didn't see a significant difference between the mean of the 3 categories. And then lastly, we can say that a total sulfur higher than 0.3 is driven by the presence of sulfide in the sample. If we take this a step further, we can say that the median of the houses that had no damage, no pyrrhotite was 0.17 weight percentage of sulfur, which this corresponds to what we call clean concrete, so like regular proportions of concrete. And we can say that a total sulfur higher than that could either be an indication of having a higher hydrated cement ratio into the mix or having trace amounts of pyrrhotite in the sample. When we look at the houses that have no damage and pyrrhotite, we can see that most of them are in between total sulfurs of 0.3 and 0.5. And then when we look at the houses that have damage and pyrrhotite in terms of their homes, all of them have a total sulfur greater than 0.3%. Now, when pyrrhotite is present, we can say that the average concentration of pyrrhotite in the houses that have no damage and pyrrhotite is significantly lower when we compare it with the houses that have damage and pyrrhotite. So for the NP houses or pyrrhotite concentration, the average was 0.66, and when we compare this to the DP houses, it's significantly lower because for them it is 1.19%. It is important to know that some of the NP houses have a pyrrhotite concentration that is higher than the average of the DP houses, but we have seen no damage in these houses. Likewise, we can also say that we have some DP houses that have lower concentration in pyrrhotite than the average of the NP houses, and we have seen damage. So a pyrrhotite concentration of equal or less than 0.5 weight percentage does not guarantee the absence of damage. Till this point, our method is able to do two things. We are able to predict the probability of damage as a function of the amount of total sulfur by itself or the age of the construction. So for example, if a house has a total sulfur of higher than 0.4, your probability of damage is greater than 80%. Or if you tell me that a house has an age of 30 years, your probability of damage is around 60%. It is important to know that the relative influence of pyrrhotite concentration cannot be determined just with this data set. We took our analysis a step closer and we wanted to see what's the influence of the age when we look at our three categories. So we can say that all DP houses, so when you see damage and you have pyrrhotite, are older than 20 years, with only 6 houses between the ages of 21 and 25. The mean age of the DP samples was 35 years. When you compare this to the NP samples, we have an average of an age of 25 years. It is important to know that we had 18 homes that were older than 25 that had no visible damage. So they were part of the DP samples. And we had 6 homes that were older than 25 in the DP category that showed some damage. When we look at the newer houses, so if we look at the blue box plot and the gray here, so likewise here, we see that there is a significant difference between the mean of the two in the DP versus the NP, and this could be a potential indication of variations in the rock mine during the times. However, when we look at older houses, so like the orange here and the yellow here, there isn't a significant difference between the concentrations of pyrrhotite and the distribution of total sulfur. So we did another step in which we divide our samples into houses that we got from Connecticut versus the houses that we have from Massachusetts. And we can see that until this point, there isn't a statistical difference between the data sets. So like the total sulfur and pyrrhotite concentrations of our samples are relatively similar. So the future direction of my research is to conduct XRD on our sample and then do very detailed field inspection into the houses that were older and had no damage. What's driving the absence of damage? Do they have waterproof basement? Is the drainage system better? Like, what are the parameters that are keeping these houses from showing the damage? Then the second step, which will be done for some of my lab mates, they're going to be performing accelerated laboratory experiments to then determine the relationship between age and damage. And then lastly, I will be using the results from steps 1 and 2 to build a predictive model for pyrrhotite-induced deterioration to help homeowners take decisions. To this point, we have 4 major conclusions from our data set. Number 1, that a total sulfur less than 0.3 equals to no damage. That the average pyrrhotite concentration in damaged pyrrhotite homes is higher than in the no damage pyrrhotite homes. However, the concentration of pyrrhotite by itself is not an indication of damage, as we have seen houses that have lower concentrations of pyrrhotite having damage, and then houses having higher concentration of pyrrhotite having no damage. We can also say that DP homes, so damaged pyrrhotite houses, are older when compared to the NP, so no damage pyrrhotite houses. However, because we have houses that are younger than 25 having damage, and then houses that are older than 25 having no damage, age alone is not a sole determining factor of the damage of the houses. And then lastly, that the 18 homes that were no damage pyrrhotite will need further investigation, as they have pyrrhotite concentrations similar to the DP homes, but they have shown no damage. Before I finish my presentation, I would like to acknowledge that this work was performed under the assistance of the United States Department of Commerce and the National Institute of Standards and Technology. Thank you.